Good afternoon, everyone. My name is Sam Schwartz with the Energy Management Association, and I'll be your moderator today. Thank you for hopping on, and special thanks to our associate member, CopperTree Analytics, who is sponsoring today's webinar. Before we get started, I'm going to cover a few housekeeping notes before we get started. The presenter is going to be answering any questions until the end of the presentation, but we do encourage you to submit questions at any time using that Q&A button. If you happen to be experiencing any technical issues during the webinar, please use the chat function to inform the panelists, and our technical experts will assist you. This presentation is being recorded and will be available for viewing within 1 week and with on-demand quiz for credit. And then finally, last note on continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. So today's webinar, as you know, is on facility management adjustments and their impact on energy management goals, how EMIS can help, with Adnan Bhatt. He has a background in electrical engineering and is passionate about working with organizations seeking to enhance operational efficiencies, reduce their carbon footprint, and improve building performance through energy management and automatic fault detection and diagnostics. So once again, thank you everyone for taking an hour out of your day to come be with EMA. And with that, we're going to hand it off to our expert today to kick off the presentation.
Thank you very much, Sam, for the introduction. And can I just confirm, Sam or any of the hosts, that you can hear me and you can see my slides?
Yes, loud and clear.
Fantastic. Welcome, everyone. Thank you for joining. I must begin by expressing my gratitude towards EMA and the entire team behind organizing this webinar. And I would also like to thank my team at CopperTree, whose feedback was critical in preparing for this presentation. So after an overview of some fundamental concepts surrounding facility management, processes like energy management systems and ongoing commissioning, and discussing tools like energy management and information systems, or EMIS, we will use some real-life examples today to see how the use of EMIS can help facility management teams to identify, diagnose, and verify energy conservation measures in an efficient and automated manner. We will address some key challenges to facility management and see how EMIS can address those challenges to continually optimize building performance. And now, though we will make a case for the role of EMIS technology as a strategic and operational tool towards proactive energy management and building optimization, we will also discuss and see the importance of how these tools need to be paired with a continuous improvement processes to become more efficient and to produce results that we desire. At the very end, we will offer some insight into how you can get started with planning and procuring of EMIS technologies. Let me begin by offering a brief introduction to our company. CopperTree is the developer of Kaizen, a powerful patented analytics tool that translates building data into useful information. Kaizen continuously acquires data from buildings, monitors system performance and energy consumption, and analyzes equipment performance to detect faults and anomalies, helping us move from a reactive state to a preventative and data-driven energy management and building optimization strategy. And just on a side note, the word Kaizen is a Japanese term that refers to the philosophy of continuous improvement. And this idea of continuous improvement is going to be a key theme of today's presentation. So our objectives for today are to, number one, gain an overview of how EMIS platforms leverages data to equip facility and energy management teams with actionable information in line with your objectives. Using some practical real-life examples, we will try to demonstrate the need for continuous monitoring of building performance and the impact of facility management adjustments on energy efficiency. Understand how EMIS platforms can establish better collaboration between energy and facility management teams and improve tracking of results and reporting, and acquire the fundamentals to build a solid business case for pairing sustainability frameworks with analytical driven solutions. And in order to achieve these objectives, we will first discuss the need for a systematic approach to facility management. Next, we will offer an overview of EMIS technologies, followed by some examples to see how FM adjustments can impact energy performance and how EMIS can help discover energy conservation measures. And lastly, we will talk about some best practices in a successful implementation of EMIS. Systematic approach to facility management. In this segment of the presentation, first we will define some key terms and go over some challenges on the path to achieving high building energy performance. Next, we will highlight the need for having a process in place. Specifically, we will talk about energy management systems and monitoring-based commissioning as a continuous improvement framework within the FM or facility management domain. So, what is facility management? According to International Standards Organization, ISO, facility management is an organizational function which integrates people, place, and process within the built environment with the purpose of improving quality of life and productivity of the core business. Therefore, the economic purpose of facility management is to add value to an enterprise through reduction of costs by implementing processes that support the core business. It is important to highlight that facility management is a holistic set of responsibilities with a key focus on people, processes, and continuous improvement. With and with rising energy costs and increasing levels of energy-related regulations and climate change policies, the responsibility of achieving a higher energy efficiency and reducing overall carbon footprint has become an integral part of facility management teams. So let's explore the typical factors that result in a poor building energy performance. And these are essentially some tasks and essentially some of the work that facility management teams have to get into. So number one, poor building conception, design, and construction. Now, this is really outside the control of facility management and operations team. But inefficiencies early on in this stage of designing or construction of a particular facility is going to impact how facility managers react to what's on site. And the reality is sometimes FM teams just have to live with and manage what's on site to the best of their ability. Non-existence, inadequate, or incomplete commissioning. Insufficient means of measuring and managing equipment performance. Now, good data is critical in implementing the right strategies and processes, and extracting that data, giving it a meaningful structure, and deriving intelligent insights is a challenge for many organizations. Poorly calibrated building management systems, lack of metering, good meter and sensor data is important to collect valuable system and energy-related information for us to be able to make better, more informed decisions about our facilities. Lack of or poor energy efficiency goals. Research has shown that there is a direct correlation between setting up higher energy efficiency goals and facility management strategies that help us achieve those goals. Poor participation from occupants and other critical stakeholders such as IT. Now, good energy management and building performance is a collaborative task. The perception that facility management and energy management are, facility managers and energy managers are solely responsible for how a building performs, this perception needs to be challenged. And all stakeholders like, senior leadership, IT, especially IT, occupants, municipalities, all need to play their part. So education and awareness around this topic is critical. Lastly, a very important and a promising point to note, research has shown that a building with good operations and maintenance practice that is poorly designed will outperform a well-designed building with poor operations and maintenance practices. Now, this really highlights the importance of implementing strategic processes and tools that empower facilities team, and help them overcome the challenges they face. And speaking of challenges faced by facility management teams, let's look at some challenges typically faced by FM teams in ensuring buildings stay optimized and efficient. The challenge of collecting, organizing, and efficiently visualizing data. We spoke about that in the last slide as well. Often energy is wasted unknowingly in operations, and sometimes inefficiencies are not captured within the building automation system or within the control system, and energy gets wasted. Limited resources and operating budgets. Facilities teams are often quite understaffed or limited on resources, and in the operational budget in a given facility is not as large as capital budget. And understaffed facilities are often often dealing with the challenge of prioritizing tasks. Tracking actions, reporting can be a tedious and time-consuming process. Occupant behavior is often unpredictable, and evolving compliance regulations and ambitious energy targets often make it challenging, make it a challenging task to keep up with building performance. In some organizations, or perhaps larger organizations where multiple stakeholders are involved, the challenge of ownership in energy management comes up as an issue. Now, who really owns the task of energy management? Is it the energy management team? Is it the facility management team? And then finally, with such inefficiencies or with such unclarity in structure, procurement processes become even more complicated, and oftentimes understaffed facility managers and facilities teams, for them to acquire new tools or go through a building upgrade or a system upgrade, the procurement processes can be tedious. And now, if you remember, when we defined facility management, ISO described it as a function that integrates processes that support a business to achieve its objectives. So next, we want to explore what kind of processes can help facility management teams overcome their challenges and improve energy performance. Specifically, we want to talk about processes and systems in the domain of energy management. So energy management systems are ways in which organizations can set and achieve objectives and energy targets in order to improve their energy performance. Now, please do note that the slide says ENMS, energy management systems. We are not addressing EMIS, energy management and information systems yet. It is important to distinguish ENMS, energy management systems, from EMIS, energy management and information systems. Energy management systems, or ENMS, focuses on strategy and processes. EMIS are the tools and technologies that help us implement these processes. So ENMS establishes and manages the human side of energy performance improvement. The ISO 50001 standard specifies ENMS guidelines that enables organizations to establish system and processes necessary to continually improve energy performance, including energy efficiency, energy use, and energy consumption. Now, this standard states that successful implementation of an energy management system supports a culture of energy performance improvement that depends upon commitment from all levels of the organization, especially top management. In many instances, this would involve cultural changes within the organization and a perception change around facility and energy management. So the ISO 50001 provides requirements for a systematic, data-driven, and facts-based process, focusing on continuous improvement of energy performance. The ENMS described in ISO 50001 is based on the Plan, Do, Check, Act continual improvement framework, and it incorporates energy management into existing organizational practices. And speaking about continuous improvement, continuous energy management, we want to next explore a ongoing commissioning process for facility management teams to streamline monitoring and implementing changes and implementing improvements within their building. So monitoring-based commissioning essentially is a continuous improvement framework. It is an ongoing commissioning process that monitors and analyzes large amounts of data on a continuous basis. And EMIS, which we will explore in upcoming slides, is essentially a tool that allows streamlining and automating the monitoring-based commissioning process. So in this process of monitoring-based commissioning or ongoing commissioning, there's an emphasis on using the meter level and system level data to continuously identify opportunities for improvements and implement and eventually implement those improvements. So monitoring-based commissioning is a data-driven process within a continuous improvement framework that hopes to improve, or that is set to improve, building performance on an ongoing basis. This slide over here, this graph really shows the impact of ongoing commissioning on building energy use and operating costs. The light blue line shows degradation of energy efficiency over time due to age of the building, changes in floor plan, occupancy levels, as equipment drifts out of specifications, lack of proper maintenance. And the fact is, buildings degrade over time. And, we can see that there are step changes, improvements in energy use as, commissioning and retro-commissioning is done on specific durations and specific, periods during the building life. And the red line shows effect of continuous commissioning on energy use as new opportunities are constantly being identified and implemented. And finally, yellow line shows the trajectory of energy performance if little or no effort is put towards managing the building performance. And now that we've gone through the importance of continuous improvement processes like monitoring-based commissioning as a facility management practice, let's talk about the tools that make this process efficient. Overview of EMIS technologies. In this particular section, we will do a quick overview of EMIS technologies and look at how EMIS and monitoring-based commissioning integrate with each other. So how do we define EMIS? So EMIS are defined as hardware and software products that comprise a broad family of tools and services to manage building energy use. So while energy management system, ENMS, and monitoring-based commissioning focused on strategies and processes, EMIS are the tools and technologies to implement these processes. These technologies, EMIS, and associated functionalities include monthly data analytics, energy information system, fault detection and diagnostic, and advanced system optimization. In essence, EIS and FDD, energy information system, and fault detection and diagnostic are the primary supervisory tools that integrate with building automation systems to provide enhanced visibility into the complex systems operating inside the buildings today. And automated system optimization, or ASO, provides two-way communication with the building automation system and works in conjunction with other tools to analyze and fine-tune BAS set points and other parameters to optimize HVAC system sequences to reduce energy usage and maintain occupant comfort. Data sources and capabilities. Data integration is a primary step when implementing an EMIS. On the left, you can see various different data sources such as building automation systems, IoT devices, weather stations, interval meters, utility bills. This data is collected at a central repository or a data warehouse, and then the data is consumed by various tools or applications that are seen under the umbrella of EMIS tools and technologies. Some of the things that we discussed in the previous slide: energy information system, FDD, fault detection diagnostics, automated system optimization, ASO. It is also important to note that different EMIS providers offer these capabilities in different ways. So at CopperTree Analytics, for example, our EMIS provides all these capabilities of monthly, EIS, FDD, ASO, and monthly data analytics within two main platforms. Our EIS platform is called Kaizen Energy, and Kaizen FDD is our FDD platform. The EIS, or Energy Information System, has energy baselining, multiple resource metering, and interactive views, while the FDD is focused on rule-based algorithms, system performance auditing, and an actionable issue management portal. And at CopperTree Analytics, the ASO is provided as a service extension to the FDD platform, so auto correction and system optimization can be further automated. Just very quickly, the difference between EIA, Kaizen Energy, and Kaizen FDD, the energy information system versus the FDD platform that CopperTree offers. So we're really trying to answer questions like, how much energy has my portfolio of buildings used to date? Is my portfolio on target to consume less than this month's baseline? What are my top performers and my worst performing buildings in my portfolio? After we implemented certain energy conservation measures, are we really tracking and seeing those energy savings that we hope for? These are the kind of questions that we hope to answer and explore using an EIS platform. Whereas with an FDD platform, what we're trying to do is we're trying to look for specific issues that are compromising energy performance, occupant comfort, and equipment life by continuously monitoring system level data. Typical analysis of excessive runtimes or simultaneous heating and cooling in certain zones, poor equipment sequencing, excessive cycling, any zones that are not achieving their set points. These are the kind of things that are typically analyzed in an FDD platform. And in our case, we use a combination of rule-based algorithms, pattern recognition techniques, system performance auditing to kind of achieve the desired objectives using these platforms. Data collection of an EMIS infrastructure. So EMIS is fundamentally a data acquisition analytics infrastructure. And while every vendor offers a different solution, many are similar to CopperTree's offering. And I'll kind of go through this slide to explain how CopperTree integrates and collects data. So the lower layer, as you can see here, is in this particular diagram shows plant, building, and zone HVAC systems, as well as lighting, access control, and other building systems. The upper layer, represents the monitoring and control infrastructure made up of the building automation system, metering system, IoT devices. And then data acquisition is achieved by integrating these different data sources, either at a building level using an edge device, or at a cloud level using data connectors deployed to access other data sources such as weather and utility data. And this data could be either inside the building or outside the building. APIs can be used for cloud-to-cloud connections to bring data in. And once the data begins to flow continuously onto our secure servers, analytical engines examine these data sets and generate reports, visualize results, and send notifications to users anytime a fault is detected or an anomaly is detected. So how does EMIS and monitoring-based commissioning work together? How do these two? How does this process and tool integrate with each other? This diagram really illustrates the monitoring-based commissioning process from data collection on the left of the slide to data warehouse, where the building data is integrated and organized. We've already described in the EMIS capabilities, which is under data analytics. But the key here is the implementation phase where a building engineer reviews the analytics and makes repairs or improvements. The resultant activity is then again monitored to track for improvements and measure savings, doing so on a continuous basis. Finally, I want to conclude this particular segment of overviewing EMIS with some stats from Smart Energy Analytics Campaign, which was a public-private partnership to encourage use of commercially available EMIS technologies and monitoring-based commissioning practices. This campaign supported 104 organizations with 6,500 buildings and I think over 1 billion square foot of combined floor area between 2016 and 2020. And the focus was to encourage the use of commercially available EMIS technologies and promote monitoring-based commissioning. And what this campaign documented was a median annual energy savings of 9% when using a fault detection and diagnostic tool, and a median annual energy savings of 3% when using an energy information system. This particular campaign also reported a investment payback of 2 years. In our experience, in CopperTree's experience, this return on investment can be expedited, and I'd be more than happy to connect with any of the participants who's interested later on to talk about how we can expedite some of this return on investment. Role of EMIS in facility management. In this section, we will look at some examples where CopperTree's FTD platform was used to monitor building performance, to identify, diagnose, and verify energy conservation measures while working with facility management teams as part of a continuous monitoring and improvement process. We will then go over some capabilities and features under CopperTree's EMIS offerings, and similar features can be expected from other EMIS platforms as well. So this first example is from a commercial facility, and what you see on the screen is a trend log view taken between late February and late March. The blue line here shows the supply fan speed for one of the air handling units at the facility, and the pink line shows the fan status. What we notice here is every time the supply fan was running, it was running at 100%. And while working with the client, it was noted that this space is unoccupied for at least 90% of the time due to construction, and that had been the case for at least a year. However, the facility manager in this particular case had been running the fan to meet some COVID-related requirements. So, right off the bat, it was a recommendation that the fan speed can be reduced, which will lead to energy savings while still meeting regulations. And while we were reviewing more data points associated with this unit, it was found that the pressure sensor reading was maxing out at 500 pascals while applying a set point of 600 pascals. Now, this indicated that either the sensor wasn't sized correctly or the internal program table wasn't set up correctly. And discussing this finding or this data point or the results with the facilities team and the controls contractor, it was confirmed that the sensor that was installed maxes out at 500 pascals. Now, this would typically result in overpressurization, as there is no way to measure over the limit of the range of the sensor, which is in this case 500 pascals. As next steps, it was recommended that the pressure set point be reduced to keep within the sensor range until it is swapped out until the sensor is swapped out for one that has a larger range. And this also helps with reducing the fan speed. So energy savings were achieved, as well as COVID-rated regulations in maintaining a certain threshold or of ventilation was also achieved. Here is another example from one of our airport clients. And the task here was to ensure that there's sufficient ventilation in order to maintain indoor air quality as per COVID-19 guidelines. the client wanted to find ways through which they can improve fresh air ventilation with more VAV airflow from fresh air intake without making huge compromises on energy. And what you see on the screen, the red line here is the trend log view for the return fan speed, which is running at 80% under normal operation. So on the left side of the graph and of the chart, and on the right end, you see normal stands for the normal operation scheme there. The fan was running at 80%. The return fan was running at 80%. The blue line represents the supply fan speed, which in normal operation was running at 100%. Now this indicates a 20% differential in fan speed. The middle section in the graph is a time frame when different fan speeds were being tested, and it can be seen that in this period a higher fan speed differential is being used with much lower return fan speeds. This next plot is a plot of VAV airflow for the durations represented in the previous slide. And what we notice here is that a higher differential of 50% or greater in fan speeds helps to supply more VAV airflow downstream. With a 20% differential, we were at around 8,000 CFM, but with the return fan speed at 30% instead of 80%, and the supply fan being at 100%, that is, now we're operating at a 70% differential, we see that the CFM increases up to 18,000 CFM. So from 8,000 CFM, we go to 18,000 CFM, changing the differential from 20% to 70%. Now, normally, with a higher return fan speed, air is exhausted faster, but that is assuming that the supply fan is running fast enough and has sufficient airflow and sufficient duct static pressure. However, in this particular case, the duct static pressure at the supply was too low to push the air through. Hence, we notice an opposite effect. So keeping the exhaust or return fan slow would help build enough pressure to supply air and thus ventilating air faster at the zone VAV boxes. So the pulling at the exhaust side needs to be matched equally to the pushing on the supply side. Otherwise, we will create a negative space pressure. So in this particular case, a higher differential of supply and return air fan is needed, and not just a higher return fan to exhaust the air out and produce more VAV airflow. So we were using analytics and visualizing the data and testing different fan speeds. We were able to achieve more energy savings by running the return fan at a lower speed. We were also able to improve fresh air ventilation, meeting COVID-19 regulations. So essentially a win-win situation. And this really shows the importance of data-driven decisions in facility management. The third example here is from a 5-story commercial facility that has been awarded LEED Gold certificate and is one of the largest commercial properties in its region. And the task here was to find out why the coefficient of performance, COP, of the chillers is not consistent. And we noticed a better COP or higher COP sometimes than other times. And how can we ensure that the chillers perform at their optimum continuously? So here in the graph, you can see how the chiller COP for one particular chiller 3 in specific, it keeps fluctuating. And now looking at one of the looking at one of these chillers as an example, we noticed that the chillers cycle about every 30 minutes or less. And it is now worth investigating if there's a relationship between chiller cycling to chiller COP and how it all relates to energy. Chiller cycling excessively can also cause more wear and tear on the equipment and impact equipment life, and can eventually become a capital expense for the organization. So what we discovered by monitoring the data points is that the chiller performance improves as the chiller stops cycling. Over here, the red line represents, the chiller cycling, and the blue line represents chiller COP. The aggregated value of performance daily is higher on days with chiller not cycling as frequently. And we can see here, how the chiller COP improves as the chiller stops cycling. For this particular chiller, we go from a COP of 4 with cycling to a COP of 5 without cycling. And it is also noticed that it takes about 3 hours for these chillers to reach their optimum COP. And in general, most equipments, perform better after running for a certain period of time. And it is, even more true in case of such large, big equipments like chillers, which take, more time to warm up than other, zone units. Therefore, our recommendation here was to rotate the chillers running whole day with a 15 occupied hour operation if needed, rather than the previous operation, which was to keep the chiller running for 3 hours and then turning off for 2 hours, and alternating between chillers within a day. This also improves equipment life and overall efficiency. This sort of analysis that we've explored in the previous slides with the 3 different examples, going through raw trend data and looking for patterns and looking for inefficiencies, this sort of analysis can be automated using an EMIS tool. The screenshot over here shows how a notification or an insight is generated for the last example in particular, indicating that the COP deteriorates as the chiller cycles, and potential cost savings are also quantified. For this particular case, we were able to identify over $20,000 per year in savings. And CopperTree's FDD platform Kaizen offers an insight management portal to all the analytical findings in a given facility and presents them in an easy to digest manner. These insights or these findings are automatically triggered after the platform detects anomalies and deviations in system performance based on continuous monitoring of system level data. Dashboards can then be customized to prioritize and filter findings based on different priority factors, such as hours of faulty operation, heating impact, cooling impact, energy impact, comfort impact, potential savings, avoidable cost, and other factors. And on the screen over here in the screenshot, we see a few different types of faults that are occurring in this particular facility. We have a fault with one of the air handling units where the mixed air temperature has deviated from set point at a higher severity than specified. We also have a cooling tower that is cycling excessively. So these kind of faults can be visualized and easily received through an issue management portal. And detailed summaries into particular issues along with a diagnosis can be automatically generated, assisting the facility and energy management teams to reach the root cause of issues quickly. Our platform also shows an insight history map indicating on what particular days was a fault active and on what particular days it was inactive. And this allows us to kind of get a better visibility and insight into specific patterns. Is this specific fault happening every Monday or every Tuesday? Or is there a particular trend of this fault? So you can kind of really dig deeper into how your facility performs. Our Kaizen, our platform Kaizen also helps users to take and track action against issues occurring in their facility. So users can assign tasks, update the status of a fault from closed, in progress, or open, add comments and tags to take control over how they want to present and respond to issues. And this facilitates better collaboration and transparency within different teams of the organizations. And for example, a team is working with a third-party contractor, they can have access to the platform as well to continuously track what's being done. KPI reports, provide great information on system performance globally. So the need to browse through individual system graphics or displays at the building management system could be a more targeted approach after viewing some of these KPI reports that are automatically generated in our platform. Here's an example of a KPI report where that indicates a percentage of time when a fan is off and the pressure sensor reading records an error. This is an automated report that shows different ACs, that compares different AC units, showing the worst performance and the best performing systems in the building. Here are some other examples of reports that can be automatically generated at a daily, monthly, or weekly frequency. The image on the left is a condenser delta T analysis report showing number of hours within a 24-hour period when the condenser is in different ranges of delta T. Red indicating, in this particular case, red indicating delta T of 0 to 5 degree Fahrenheit. So lots of low delta T for this particular unit between July 1st and July 10th. The image on the right is a plot of chiller runtime with outside air temperature, and the raw data is also displayed in the table below. And you can see how the green line there corresponds to chiller 2. So chiller 2 has consistently higher runtimes than other chillers in this facility. Now, as part of continuous monitoring and measurement of data, teams must be able to easily review performance metrics and verify the impact of energy conservation measures. It is important to be able to analyze energy use and consumption across a building or portfolio of buildings, identify significant energy users, reach and get to the worst performers quickly, prioritize opportunities, and continuously report on them. The screenshot that you see on the screen is from the resource management feature in our EIS, or Energy Information System platform, Kaizen Energy, which allows different energy sources such as electricity and natural gas to be monitored and tracked separately. Water consumption, as well as sources feeding specific equipment, can be configured as individual meters, each with the right and the appropriate unit selected. So, for example, in this particular case, you see there's a main electricity consumption meter. There is a more targeted HVAC equipment electricity consumption meter displayed as separately, and then you have water consumption, gas consumption, and heating water consumption meters shown displayed on the dashboard. Here's another example where cumulative performance over a selected period of time is shown, and this really gives users visibility on how their building's consumption compares to established baselines. It also highlights a day-by-day breakdown where the consumption was worse or better than the baseline, and this type of visualization is a must if a facility desires a more proactive approach to achieving energy savings. Another two reports or two views. The one on the left shows a consumption distribution chart showing the contribution of each building in a given portfolio to the total energy consumption. And on the right side, you have a consumption breakdown chart that shows each building's consumption per day for the month of March 2021. So our EIS platform, Kaizen Energy, also has a versatile baseline functionality where users can choose, simple historical data to compare, for example, current energy consumption against, same time last year, or use a linear regression model where we use historical data with one or more independent variables to adjust the baseline as it correlates to occupancy or weather. And shown in this slide is the linear regression modeling for buildings energy baseline using historical consumption data and using two independent variables. In this particular case, we are using heating degree days and CO2, which is an implicit occupant sensing device. So, keeping our learning objectives in mind as we approach the end of the webinar or this part of the presentation, I hope this presentation has helped to highlight how tools like EMIS technologies, when paired with ongoing and monitoring-based processes, can help with better building and energy data management. Clear and structured visibility into building systems and energy performance. I hope it was clear how EMIS empowers facility and energy-related staff and brings leadership into the continuous improvement and continuous energy improvement process. How EMIS supports facility and energy management teams with low resources by prioritizing tasks and tracking action. Intelligent automated insights help us move from a reactive maintenance to a proactive and predictive maintenance, allowing organizations to save energy and money. Automated reporting with better visualization of building performance, KPI monitoring also results in time and cost savings and better visibility for an organization. Improved occupant comfort, making sure indoor occupant comfort and occupant health and safety are top concerns for organizations, especially with the recent pandemic. So monitoring indoor air quality, monitoring performance of systems against guidelines from CDC and ASHRAE can be simplified using an EMIS tool. Quality assurance and risk management, keeping up with regulations and compliances is another benefit of using an EMIS, and ongoing commissioning process. And finally, bridging the gap between energy management and facility management for better collaboration and transparency. So getting started, this is the last slide here, and I wanted to conclude this presentation by offering some practical steps that can help you and your organizations plan and get started with the deployment of the tools and the processes to improve building performance, save energy, and improve occupant comfort, while empowering and supporting facility and energy management teams, and not adding up to their list of tasks. So it's important to remember that EMIS planning is part of overall planning for an energy management system. An EMIS tool, or any tool under the scope of EMIS, if implemented without a process, will not result in desired objectives or desired results. So step number one is to establish and set up the goals. What exactly does that organization, where exactly does that organization want to be within the next 1 year, 2 year, 3 year? What compliance regulations do we want to meet? Understanding and setting up these goals is really important. Establishing roles and responsibilities. Again, this is really important. Division of responsibilities. Getting all the right stakeholders involved. Ensuring a organization's IT and senior leadership is fully looped into the process and the planning, and everyone understands their responsibilities and how they contribute towards this program, towards this system. Next step is to design the EMIS capabilities and scope. Step number 4 is to establish feasibility, understanding the costs associated with external costs of any sort of tools and processes, and internal costs and internal labor costs that will be required to put in if a ENMS and EMIS are to be implemented in a facility. And then implementing the energy management system, implementing the process on the human side is extremely important. Documenting the entire process of setting up goals, responsibilities is critical. Finally, procurement of an EMIS tool. Procurement can be a hectic process. So, at CopperTree Analytics, we try to work with different joint purchasing programs in different states, or different incentive programs offered by utility companies to help organizations and teams procure tools and technology that can help them achieve their objectives towards sustainability objectives. There are also a lot of existing EMIS specifications and procurement support materials that organizations can leverage. For example, the reference I mentioned in this slide by the Office of Energy Efficiency and Renewable Energy, they offer detailed guidelines on how can you get started with planning and procuring EMIS. Other organizations also offer sample templated EMIS specifications and support materials that an organization can leverage and not start in the blind. Again, with that, I conclude my presentation. Thank you very much for your patience, and we open up to questions now.
Thank you very much. If anyone has any additional questions, feel free to put them into the Q&A chat. But before we start our little Q&A session, I do want to make sure that we play a quick ad, and then we will be right back.
CopperTree is on a mission to make sure that smart buildings deliver on their promises. Our AI software, Kaizen, continuously monitors your building's performance, alerting you if a fault is detected or if performance is suboptimal. With no upfront capital investment and an affordable software as a service usage fee, Kaizen results in time and resource savings for facility managers and cost savings for stakeholders. We deliver a comprehensive building analytics solution consisting of an energy information system, a fault detection and diagnostics platform with integrated system performance auditing. Our clients successfully use this powerful tool to move from a reactive or preventative maintenance model to a data-driven, proactive maintenance approach. CopperTree Analytics can help you create operational efficiencies, reduce your building's energy consumption, and improve your bottom line.
Okay, and feel free to share your screen again. I'm going to hop into a question that we have here. What if the building MEP system does not have the proper metering or metering measured mixed loads? How can we deal with such a case?
Thank you for that. Thank you for that question. And we see that on many projects, and this is the reality on some sites where there isn't sufficient metering or good meter data is not available, or there's just lack of quality data on sites. And as CopperTree Analytics, we try to make the best out of the project that we have. We also leverage something called virtual metering. For example, if we can get if we can access system level data and get our hands on equipment drawings and equipment data sheets, understand equipment ratings, we can use different data points such as amperage and horsepower rating and whatnot to calculate energy consumption of specific equipment and output that as a virtual meter in our platform. And oftentimes, for organizations to get into the granularity of energy data for some of their systems and subsystems, installing submeters or installing submeters can become an expensive task. And that is where we can leverage the use of virtual metering. And again, even deploying virtual meters at the end of the day would depend on the availability of overall data for a particular system or a particular unit in the facility.
Thank you. And then this next question we have, you spoke of rule-based algorithms for your FDD platform. Who creates these algorithms? Do users have the ability to create their own or modify them?
Yeah. So thank you for that question again. At CopperTree Analytics, CopperTree offers a complete turnkey solution when we work on projects. So CopperTree creates these rule-based algorithms. Our team of engineers creates these rule-based algorithms. However, we use a very flexible visual programming user interface to create these algorithms. And we can train end users or any of our partners on creating or modifying the rules that are created by CopperTree. Within our platform, we also have a community library of algorithms and rules with, I think, over 4,000 algorithms. And these algorithms are a mix of rules that are created by CopperTree staff and some of them created by our partners and end users. And it's available to all users of Kaizen to look through and clone or modify and implement in their own facilities. And like I said, just because we don't use any line code based programming and we have a visual block, user interface for creating these algorithms, it is very easy for a user to be trained on how to create or modify these rules.
Okay, so those are all the questions that we have today. So thank you very much for coming on and walking us through this for an hour. Very enlightening. Thank you.
Thank you very much.
So we do have another presentation coming up, led by Charles Jackson, who is actually on the board of the ABC commissioning group, and two of his colleagues will be joining him to talk about transforming a White House parking garage. It was a big sustainability project, and he's going to walk through the lessons learned from that. So we hope to see you there. And everyone, enjoy the rest of your day, and thank you for stopping by with EMA.